In this chapter, we're going to be doing radical reactions, meaning radicals are going to be the intermediates along the reaction pathway. So for that reason, it's important that we have an understanding of radical stability to know if a radical is even possible for forming or to analyze intermediates to figure out a preferred reaction pathway. The nice thing about radicals is they follow the exact same trend as carbocations. And that should make sense because radicals are electron deficient, like carbocations. Here I have a series of radical intermediates in order of increasing stability. And here at the very bottom, the least stable is when we have a radical on a double bond. This is a vinyl radical. We've talked about the vinyl cation as being incredibly unstable, and the same is true for the vinyl radical. Then a little bit more stable than that is to have a radical on a methyl group. So this is our methyl radical. Next we have a radical on a carbon, and that carbon is bonded to one carbon. So that we would call a primary radical. Next we have a radical on a carbon bonded to two carbons. That's secondary. Then a radical on a carbon bonded to three carbons. That's tertiary. So the reason we see increasing stability in going from the methyl to the tertiary radical is because we're increasing substitution. And for the same reason substitution stabilizes carbocations, substitution stabilizes radicals, and that is due to hyperconjugation. Then moving on, we have a radical next to a double bond. This is called an allylic radical. And we have something very similar to an allylic radical where the radical is next to a double bond, but it's a double bond of an arene or of benzene. This is called a benzylic radical. And the reason that these two are at the top of the list as being the most stable is because of resonance. Let's look at how we can draw a resonance structure for the allylic radical. So remember that this pi bond is really two electrons. So what we can do is take this electron right here, the radical, and I'm going to move it into the bond, and I'm also going to move one of these electrons from the pi bond into this bond on the right, and pair those up. When we pair those up, we get a new pi bond there. And then this other radical here will go into this carbon as a new radical. So here is our pi bond. It's made up of the blue electron and the red electron, and then this blue electron will just be on this carbon. So that's how you get the resonance structure. For the benzylic, I'll just show you one resonance structure for this. So here we can take an electron from this pi bond, pair it with this radical, and then we'll put an electron here. Oh, and I should have had a resonance arrow on that first example. When we do this, we get a double bond there and a radical here on the ring. We can use radical stability to predict bond strength. And our guidelines here is that weaker bonds will break to give more stable radicals. So if we look at propane, and I've highlighted specifically two different hydrogen in propane. One is on a primary carbon, one is on a secondary carbon. And the question is, which of these two CH bonds is stronger? So to figure this out, what you want to do is actually break this and look at the resulting products. So this is just kind of a hypothetical that we're doing. If we break this primary CH bond, we get this radical and the hydrogen atom. If we break the secondary CH bond, we get this radical and the hydrogen atom. The radical on the right is secondary, the radical on the left is primary. We know that the secondary radical is more stable. Since this CH bond yields something more stable, it's easier to break. If it's easier to break, it's weaker. This will be important when we go to do reactions because we're going to have to predict which CH bond is broken, and we're going to pick the one that is easiest to break. That will be the one that ends up giving us the product.